the ratio and root tests. The ratio test is a test for convergence that we can use on any series. It doesn't always give a conclusion, but it often will. And you'll find that this is one of the most useful tests of all the tests for convergence for series. The process is we take the limit as n goes to infinity of the absolute value of the n plus 1 term divided by the nth term of a series. Suppose this limit is equal to some number L. If this number L is less than 1, then we say the series is absolutely convergent, and therefore convergent, of course. If this number L is greater than 1, then we know the series is divergent. And if this limit is equal to 1, the ratio test is inconclusive. And that means that there is no conclusion that can be drawn about the convergence or divergence of the series, and therefore you would need to use a different test. Let's take a look at a couple of examples. So here we wish to test the series for absolute convergence. First, I want to point out that the nth term of this series is negative 1 to the n times n cubed divided by 3 to the n power. And the n plus 1 term of the series is going to be basically the nth term, but you are going to replace n with n plus 1. So we'll have negative 1 to the n plus 1 times n plus 1 to the third divided by 3 to the n plus 1 power. And to use the ratio test, we are going to take the limit as n goes to infinity of the absolute value of the n plus 1 term divided by the nth term. Another way to think of this is the limit as n goes to infinity of the n plus 1 term multiplied by the reciprocal of the nth term. This is actually kind of nice to think of it this way because it will save you a little bit of time. So what we have here is the limit as n goes to infinity of the n plus 1 term multiplied by the reciprocal of the nth term. Now, one thing we can do right away is apply the absolute value to everything inside of this. So since all of these are multiplied and divided together, we can take the absolute value of every single one of these independently. And the main thing to point out here is that when you take the absolute value of negative 1 to the n plus 1, this is always going to be equal to 1. Likewise, the absolute value of negative 1 to the n is always going to equal 1. So for this reason, you can pretty much ignore these alternating factors when you're using the ratio test for absolute convergence. So we'll just get rid of these. Now we have the absolute value of everything else that remains, but all of these quantities are already positive. So at this point, we can simply remove the absolute value symbols. And what we have is n plus 1 to the third times 3 to the n power divided by 3 to the n plus 1 power times n to the third. And now using properties of exponents, 3 to the n will cancel out all the factors of 3 in the denominator except for one factor. So we are going to have a 3 in the denominator left over. That can be factored out of the limit as a constant, 1/3. And then the other two factors here can be combined. N plus 1 over n quantity to the third power. And again, this is just a property of exponents. So now we're going to use properties of limits, which tell us that we can bring the limit inside of the third power here. So we have the limit as n goes to infinity, n plus 1 divided by n, quantity to the third. And now the whole problem just comes down to calculating this limit. Well, of course, we know that the limit as n goes to infinity of n plus 1 divided by n is equal to infinity divided by infinity. Therefore, we can apply L'Hopital's rule and take the derivative of the numerator and the derivative of the denominator, and this limit is going to equal 1, which means this result is going to be 1/3 times 1 cubed, and this, of course, is 1/3. So this is our value of L, where L represents the limit that you get when you use the ratio test. And since this number L is less than 1, we know that this series is absolutely convergent. Which of course means that it's convergent as well. In our next example, we have the summation of n to the n divided by n factorial. And you'll find that the ratio test is really good at dealing with series that have a factorial. Let's remind you what it means to be a factorial. So for example, if I have 6 factorial, this means 6 times 5 times 4 times 3 times 2 times 1. And in the case where you have a number, of course, you can multiply this out, and this number would be 720. When you have something like n factorial, you're going to start with the number n, and you're going to multiply it by the number that is 1 less than n, which is n minus 1. And then you'll multiply that by the number that is 1 less than n minus 1, which is n minus 2. And you continue this process until you get all the way down to the number 1. And we can do this for any type of factorial. So for example, if I have n plus 1 factorial, this is going to be n plus 1 times the number that is 1 less than n plus 1, which is n, times the number that is 1 less than that, etc. But again, you can do it for anything. So for example, you could have 2n plus 3 factorial. And this would be 2n plus 3 times the number 1 less than that would be 2n plus 2 times 1 less than that would be 2n plus 1 times 2n minus 1, etc. Okay, so I hope you get the idea here with factorials. It is very useful sometimes to write it out in terms of its definition. And one other thing about factorials is we can do this. So for example, if I have 6 factorial, we know that it's 6 times 5 times 4 times 3 times 2 times 1. But if it suits me, I can always put a factorial at any point in this process. So let's suppose I put 6 times 5, and then instead of saying 4 times 3 times 2 times 1, I could just put 4 factorial, right? So for example, if I have 11 factorial, this is going to be 11 times 10 times 9 times 8, and then if I feel like it, I can always just put a factorial to represent the rest of it, okay? So this is another very useful property with factorials. All right, let's go ahead and get back to our problem now. So in this series, the nth term, an, is going to be n to the n power divided by n factorial. And the n plus 1 term will be n plus 1 to the n plus 1 power divided by n plus 1 factorial. And for the ratio test, we are going to take the limit as n goes to infinity of the n plus 1 term multiplied by the reciprocal of the nth term, which is going to be n factorial over n to the n. Now, let's rewrite this as the limit as n goes to infinity of n plus 1 to the n plus 1 over n to the n times n factorial over n plus 1 factorial. And I can remove the absolute value here because everything inside of the absolute value is already positive. So the absolute value isn't doing anything in this particular problem. Now, how can we simplify this? So let's remember just a few moments ago, we mentioned that if I have something like n plus 1 factorial, I can write this as n plus 1 times n, etc. So if I want, I can put a factorial there. So let's go ahead and replace m plus 1 factorial with this expression. Now, once I do that, you can see that these n factorials here are going to cancel out. And so what we have now is the limit as n goes to infinity of n plus 1 to the n plus 1 divided by n to the n times n plus 1. And just for effect here, I'll remind you that this n plus 1 in the denominator is to the first power. Now what I can do, if you notice, we have n plus 1 to a power here. We have n plus 1 to a power here. So if I have that, n plus 1 to the n plus 1 divided by n plus 1 to the 1, we can write this as n plus 1 to the n plus 1 minus 1. And all I'm doing here is taking the top power minus the bottom power. And of course, this is n plus 1 to the n. So basically, this n plus 1 in the bottom cancels away one of the factors of n plus 1 in the numerator. And so now we can write this limit as the limit as n goes to infinity of n plus 1 to the n over n to the n. Let's keep on going. We can combine these under a single exponent. So we can say n plus 1 divided by n quantity to the nth power. And I'll go ahead and express this as the limit as n goes to infinity of 1 plus 1 divided by n quantity to the n. And all I'm doing here is dividing each of these by the denominator n. Now, how do we calculate this limit? Well, as n goes to infinity, this goes to 0. And so the inside of the parentheses is going to be 1. And of course, n is going to infinity. And so we get 1 to the infinity power. And this is an indeterminate. So how do we deal with this type of limit? Well, what we have to do is take a natural log of that expression. So I will remind you that 1 plus 1 over n to the n power is equal to e to the natural log of that expression. And so when we take the limit as n goes to infinity of this, that is the same as taking the limit as n goes to infinity of e to the natural log of 1 plus 1 over n to the n. Now what I can do is I can bring the limit inside of the exponential function and apply it to the natural log. So this becomes e to the limit as n goes to infinity of the natural log of 1 plus 1 over n to the n power. And so our answer here is going to be e to the power of whatever we get for this limit. And so now we're just going to focus the rest of our time here on calculating this limit. So let's go ahead and do that. We have the limit n goes to infinity of the natural log of 1 plus 1 over n to the n. The first step here is we're going to take this power of n and bring it down in front of the natural log. This is a property of logarithms. And then we can rewrite this as the natural log of, oops, this is not here. Sorry about that. So we have the natural log of 1 plus 1 over n. And instead of multiplying by n, I'm going to divide by 1 over n. Now, as n goes to infinity, we get the natural log of 1 on top, which is 0, and we get 0 in the bottom. So now we can say this is equal to, from L'Hopital's rule, the limit as n goes to infinity, and we are going to take the derivative of the numerator and the derivative of the denominator separately. So the derivative of 1 over n is negative 1 over n squared. The derivative of natural log of anything is 1 divided by that thing multiplied by the derivative of this thing. And the derivative of 1 plus 1 over n is negative 1 over n squared. And so this is very convenient because this and this will cancel out completely, and we end up with the limit as n goes to infinity of 1 divided by 1 plus 1 over n. But we know that 1 over n goes to 0 as n goes to infinity, so we get 1 divided by 1 plus 0, which is 1. Okay, but the limit isn't 1. Remember, we took the natural log, but we also had e to that power. So whatever we get for our limit here has to come back in and be substituted. And so our final result here is the limit is equal to e to the 1. And of course, e to the 1 is e. So what that means is that our limit of our ratio of the two terms is equal to e. And e is bigger than 1, therefore this series is divergent according to the ratio test. Part 3 of the ratio test says that if the limit is equal to 1, then the test gives no information or no conclusion. Let's apply the ratio test to each of these series. So we'll start with the harmonic series, summation n equals 1 to infinity of 1 over n. Notice that an is 1 over n, and an plus 1 is 1 over n plus 1. And so the ratio test says we take the limit as n goes to infinity of the absolute value of the n plus 1 term multiplied by the reciprocal of the nth term. And this is the limit as n goes to infinity of n divided by n plus 1. The absolute values here are unnecessary. And this limit is clearly equal to 1, which means there is no conclusion from the ratio test. For the other series, summation n equals 1 to infinity of 1 over n squared, we have an nth term of 1 over n squared, and our n plus 1 term is 1 over n plus 1 squared. Applying the ratio test here, we get the limit as n goes to infinity of the absolute value of the n plus 1 term multiplied by the reciprocal of the nth term. Again, the absolute values here are unnecessary, and we end up with this limit. And of course, we can multiply this out. There's actually a few different ways we could calculate this limit. But what we have here is n squared over n squared plus 2n plus 1. And again, this limit is equal to 1. So the ratio test gives no conclusion for both of these series. So what I'm trying to show you here is that the ratio test won't always work for every series. In fact, it doesn't work for these two series, and these are really basic series. So the emphasis here is that you still need all of the other tests that we learned. So for example, we know that this series is divergent because it's the harmonic series. And we know that this series is convergent because it's a p series with p equals 2, which is bigger than 1. So don't forget your other tests for convergence. The cousin of the ratio test is the root test. The root test involves taking the limit as n goes to infinity of the nth root of the absolute value of the nth term. And again, we're going to call this limit L. Now, the nice thing about the root test is the conclusion is exactly the same as the ratio test. So if L is less than 1, then your series is absolutely convergent. If L is greater than 1, then your series is divergent. And if your limit equals 1, the root test gives no conclusion. Now, to be honest with you, you won't use the root test very often because the limit itself is often more difficult to compute than the ratio test. but there are some instances where the root test is very easy to apply. Let's take a look at a couple of examples. So here we have the series summation 2n plus 3 over 3n plus 2 quantity to the nth power. So one indication that the root test might be the test you want to use is when you have something raised to an nth power, or you could even raise it to an n squared power or some other variable power. Why does the root test work so well here? Well, let's go ahead and apply it and we'll see why. So the root test says take the limit as n goes to infinity of the nth root of the absolute value of an. And so for this problem, we have the limit as n goes to infinity of the nth root of the absolute value of this. Now, one thing that's nice about this is this expression is positive already, so the absolute value is something that we can actually remove. So if we just ignore these absolute values here, notice that you have an nth root and you have an nth power. And you should remember that an nth root of something to an nth power just gives you whatever's inside. And this is if that thing inside is positive, which it is. So this just simply becomes the limit as n goes to infinity of 2n plus 3 over 3n plus 2. And this limit is 2/3, which is less than 1. Therefore, this series is absolutely convergent, according to the root test. So when you have that power here on your original, that's a good indication that the root test is going to be easy to use. Now, like the ratio test, the root test does not always work. Let's consider this example. So if we apply the root test to this problem, we have the limit as n goes to infinity of the nth root of the absolute value of n divided by n plus 1 quantity to the n power. Once again, this is already positive, so these absolute values don't really need to be there. And once again, the nth root and the nth power are going to cancel out. And this will give us the limit as n goes to infinity of n divided by n plus 1. And this limit is equal to 1, which means from the root test, there is no conclusion here. So to determine whether this series converges or diverges, we have to apply a different test. And the test we're going to apply here is just going to be the divergence test. What happens if I take the limit as n goes to infinity of the nth term? So n divided by n plus 1 to the nth power. Well, what you get here is 1 to the infinity. And so we can evaluate this limit by doing a natural log, right? So n divided by n plus 1 to the nth power is equal to e to the natural log of that thing. So this is very similar to what we did just a few moments ago. And now when I take the limit of this, we're going to have the limit of e to the natural log of n divided by n plus 1 to the n. Then we are going to move that limit inside of the exponent here. The next step is to take this power and bring it down. And then we are just going to focus on this limit. And so what we have there is the limit as n goes to infinity. And I have the natural log of n divided by n plus 1. And then this n in front we are going to put in the denominator as a 1 over n. And this limit is 0 divided by 0, which means now we can apply L'Hopital's rule. And this becomes the limit of the derivative of the denominator. And then we also need to do the derivative of the numerator. Well, the derivative of natural log of anything is 1 divided by that thing. And then we have to multiply by the derivative of that thing. So n divided by n plus 1, the derivative of that. Quotient rule says bottom times derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. And if you simplify this, you will find that you get 1 divided by n plus 1 squared. Okay, so now we're just going to work on this. So this is equal to the limit as n goes to infinity. 1 divided by n over n plus 1 is the same as n plus 1 over n. Then we have multiplied by 1 over n plus 1 squared. And I'm going to bring this up to the numerator as negative n squared over 1. And let's see what we can do here. Well, we have an n plus 1 here. That's going to cancel out one of these factors. We have an n here, which is going to cancel out one of these factors. And so we end up getting the limit as n goes to infinity of negative n over n plus 1. And this limit is negative 1. So, going back to here, our limit is going to be e to the power negative 1, which is 1 over e. Now remember what the divergence test says. If you take the limit of the nth term and you get something that is not 0, this means your series diverges. So the divergence test tells us that this series diverges because the limit of the nth term was equal to 1 over e. So just as with the ratio test, in the root test, it's not always going to work, so you will need to remember all of the other tests for convergence and divergence that you've learned up to this point. And that concludes this video lesson.